Our second way of calculating the overall delta H for a reaction is using Hess's law. Hess's law takes advantage of the state function nature of enthalpy. If we can express a reaction as a sum of several other equations, then we can find the overall delta H, the overall enthalpy change, by adding the delta H's of each of those equations that add up to the full one. If we know the steps, we can add up the steps to get the final value. Hess's law is another way that we can calculate enthalpy when we can't measure it in the lab, or we just don't want to. We can use it as long as different reactions have been measured in the lab that are appropriate to our calculation. Here is a simple Hess's law example. With the formation of CO2, we've seen that the equation can be written as 1 carbon plus the O2 molecule makes CO2. The delta H for that reaction is negative 394 kilojoules. We can think of this reaction as a two-step process, where each step is adding on an oxygen. The first step is carbon plus 1 oxygen, but we can't express it that way in our equation because we still need it to be expressed as an enthalpy of formation type of equation, in which there is a coefficient of 1 on the right-hand side, and elements the way we find them in nature on the left-hand side. This particular equation is written as carbon plus 1/2 of the O2 molecule, which is equivalent to 1 oxygen atom, yields the CO molecule. The measured enthalpy of formation of carbon monoxide is negative 111 kilojoules. In the second step, we can add on 1 more oxygen. Again, we would be adding it in the form of 1/2 the O2 molecule, and it would produce CO2 gas. The measured delta H for the second step is negative 283 kilojoules. If we add the delta H values for the steps, negative 111 plus negative 283 gives us a total of negative 394, which is the same as the measured delta H for the reaction of carbon and the O2 molecule to get CO2. We can add the equations together for the two steps in the same way as when we add our redox half reaction equations together. Anything on the left side of an arrow goes down on the left side of the arrow. Anything on the right side of an arrow goes down on the right side of the arrow in the overall equation. If something appears on both sides, we can cancel it out. In this case, with our two steps, the CO appears on the right side in the first equation and on the left side in the second equation, so that ends up canceling out. We can just bring everything else down on the correct side of the arrow. On the left, we have carbon solid and 2 of our 1/2 O2s. 1/2 plus 1/2 makes 1. So in our final equation, we have 1 O2 molecule. On the right side, we have our CO2 gas. After adding our two equations together for our two steps, we add the delta H's together for the two steps, and that gives us the same delta H that was experimentally measured for the overall equation. We can look at a diagram for these reactions. Essentially, there are two ways to get to the destination of forming CO2. We could go there directly with carbon and the O2 molecule going to CO2, or we could do it in steps, where we have carbon plus 1 oxygen, and then we add another oxygen to that. Both ways take the same amount of enthalpy, since enthalpy is a state function. Remember our rules for delta H. We're really going to apply them a lot in this section. If the coefficients in an equation are multiplied by some value, then the associated delta H has to be multiplied by that same value. Let's look at an equation. 1/2 of the nitrogen molecule plus the O2 molecule makes NO2 gas. Let's say we wanted to manipulate that equation by multiplying each coefficient by 2. 1/2 times 2 is 1 in front of the N2. 1 times 2 is 2 in front of the oxygen, and 1 times 2 is 2 in front of the NO2. We've multiplied our equation by 2. Each of our coefficients got multiplied by 2, so we must do the same thing to our delta H. Delta H was originally 33.2. We multiply that by 2, and that gives us 66.4 kilojoules for the manipulated equation. Our other rule is that if you reverse the equation, the sign on the delta H also has to be reversed. That is, change from a positive to a negative, or negative to a positive. Let's say we have the equation for the formation of hydrochloric acid. H2 plus Cl2 yields 2HCl. It has a negative value for delta H. If we reverse the equation so that the HCl is on the left and the hydrogen and chlorine are on the right, we're going to change the sign on delta H so it becomes positive 184.6.